Hey, welcome back to Math with Patrick and Quill. Today is August 3rd, and we're solving problem number 215 from the Daily Epsilon calendar. And we should figure out why the answer for this problem is 3 today, because that matches today's date. So we have that x, which we're solving for, so hopefully x is 3. X is equal to the cardinality, or the size, of the set of the divisors of 7 factorial plus 1. I guess I could write this as like maybe d such that d divides 7 factorial plus 1. Having this kind of double vertical bar notation here is a little bit silly, but hopefully this is legible to you as I was reading it out loud. Essentially, we're just trying to figure out how many divisors, I'm calling d, and then this vertical bar you can also use to denote divides, and then 7 factorial plus 1. So I think what I want to figure out first is just what this number is. It's kind of hard for me to figure out divisors of a number without knowing what the number is already. So also a little question mark here. We both, know from the calendar that the answer is supposed to be 3, but currently I'm not quite sure. So that's why I put a little question mark up there. Well, we could still find the cardinality of the set of the divisors d that divide, and then I'm going to rewrite that number right there. And let's try to figure out what 7 factorial plus 1 is. So factorial just means to start at this number 7 and multiply down to 1 all of the natural numbers, essentially. So for 7 factorial, we're going to do 7 times 6 times 5 times 4 times 3 times 2 and then times 1. And then, yes, that times 1 doesn't really do much, but just kind of like by definition, that times 1 is still included. And finally, we're going to add 1 because that's what the problem says to do today. So 1 times 2 is 2, times 3 is 6, times 4 is 24, times 5 is 120, times 6 is 720, and times 7 is not something I can do in my head. Although I think we're going to get 140 out of the 7 times 20, and then 4,900 out of the 7 times 700. So if I add these components together, I will get 5,040. So this number is going to be 5,041. Okay, so now we need to figure out how many divisors this number has. And when searching for divisors, let's just pick a smaller number for now just to kind of like make some sense out of it. Basically, we need to find some whole numbers where when we divide our original number by that whole number, we'll get another whole number back. So this division problem here shows that 2 is a divisor of 12, or you could even think that 6 is a divisor of 12 and we get 2 back. So usually our divisors come in pairs. So you could divide 12 by 1 and you get 12 back. You could divide 12 by 3 and get 4 back. And for most numbers, you'll find that you'll have an even number of divisors. Like if we just pick another number kind of at random, let's say 18, we'll go 1 and 18, 2 and 9, 3 and 6, and then we have an even number of divisors. So I'm cheating a little bit because I can see today's date is 3, and that's odd. And the only way to get an odd number of divisors is if one of our pairs has the exact same number in both spots right here. Because like we wouldn't want to double count the number, even though it shows up here and here. Like if it's the same number, then we should just count it once. So for example, let's pick a square number like 25. We can see that 1 and 25 are some factor pairs, and then 5 and 5 also work to multiply to 25. But when I'm counting up the number of divisors, it just wouldn't make sense to double count that 5. There are just 3 numbers that can evenly divide 25. So that means that, again, cheating a little bit, knowing the answer is 3, That means that 5041 has to be a number like 25, where we take some prime and square it, and then we would get that prime, the number itself, and then 1 as our only divisors. So we could try figuring out what the square root of this number is, and then basically we have found all 3 of our divisors. How do we figure this out, though? So I'm trying to figure out like a number multiplied to itself that gets kind of near 5,000. Like if I try like 100 times 100, I would just get 1 with 4 zeros past it, which is twice as big as 5,000. So I know that 100 is too big of a number to kind of get squaring it to get to 5,000. I could try like a lower number like 50. If I square 50, I'm going to get 2,500. So it looks like I'm kind of in the middle here. Like if I double 2,500, I'm roughly getting 5,041. And if I double that again, I'm roughly getting 10,000. So maybe a good guess would be like 75 squared. And let's just try some numbers around maybe 75, maybe 70, just to see ballpark where we should be. 70 squared is going to be 4,900. Actually, that's really close to 5,041. So maybe let me actually just try 71. This will be the previous square, and then it looks like I should add on a 70 and a 70 and a 1. I'm kind of imagining an area model right now, where if I do 71 times 71, then here's my 4,900, here are both of those 70s, and here's that 1. So this shows me that 71 squared is going to be, 5,041. Okay, well, that's cool. And so 5,041 can factor into 71 and 71. 5,041 can also factor into 1 and itself. And that's about it. 1, 5,041, and 71 are our 3 divisors of this number. So we could rewrite our set as just those 3 numbers. So if we're trying to find the divisors such that that divisor divides 5,041, then we could just rewrite this set with those 3 numbers directly. 1, 71, and 5,041. And we could write it like this. And then the cardinality of this set is just 3. Just to be sure that there are no more divisors, we should probably factor the 71, or at least try to factor the 71. Because if we find more divisors of 71, then those would be divisors of our original number. However, if we don't find any other divisors of 71 besides 1 in itself, or if we find 71 to be prime, then we know that there are no more divisors of this number. So we should check the divisibility of 71 by a few of the smaller primes. 2 is not going to work because this is an odd number. 3 is not going to work. The nearest multiple of 3 is 72. 5 is not going to work because it does not end in a 0 or a 5. 7 is not going to work because the nearest multiple of 7 is 70. And then 11 isn't going to work because the nearest multiples are either 66 or 77. And that kind of hops the 71. And when you're searching for divisors of larger numbers, you really only need to count up to the prime that when you square it, actually when you square it goes under the target number. So I actually only needed to go up to 7 because 7 squared is 49. And then 11 squared is 121. I overshot the 71. And so just with this procedure, you don't actually need to check this next number. But I guess maybe I checked it for good measure. So anyhow, 71 is definitely prime. That does mean that these are the only 3 divisors of 7 factorial plus 1. And so since I have 3 numbers in my set, that means that our size of the set is 3. So x is equal to 3, and we're all done. So thanks for coming along and watching this video, and I'll see you in the next one. Bye.